Right. Remind me in like 2 minutes, just in case I forget. If I don't start talking about it, I mean. Oh, and thanks, because I had totally forgotten. Yeah. How come nobody sits over here anymore? Well, no, I was observing that a lot of people sat on that side. Echo, 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 echo. I asked, it was a question. Echo, echo. It was more a question, not a statement. Because I just always assumed that all the cool kids sat at the back of the bus. But when I started trying to sit in the back of the bus, I didn't actually feel cooler. Actually, I probably felt more out of place. So I'm not certain. But you do have to walk by all these seats to get to those seats. So I should ask these guys, why do you sit on this side? Is my profile better on the left side? First day of class, yeah. I actually had a professor that on the first day of class, he said, everybody sit where you're going to sit for the rest of the term. And so if you're going to go move, if you want to sit next to your friends or something, get up and move now. And so I guess a few people got up and moved. And then he took pictures. I told you this on the first day, right? Yeah. Whose name do I remember? So prior to this class, I might have forgotten Pryor's name. Oh, come on. You have to laugh at my jokes, even when they're stupid puns. You know that laughing at my jokes is worth way more extra credit than any extra credit assignment could be worth, right? That was good. If I only knew your name. Tucker. All right. Today's topic is design for manufacturability. And it is has been this concept of design for manufacturability. It has been the bane of my existence for the past, I don't know, 30 years. I wanted to say 20, but then I realized I was older than that. 30 years. And so I know I asked at the beginning of the class, but raise your hand if your intent in life is to design stuff. If you want to, and so that's, I guess about half of you sort of have your hands sort of up. Because I had the kid that lived across the hall from me freshman year. His goal in life was to be an inventor. And so he studied mechanical engineering here at WPI because he knew that he had ideas, right? And he wanted to invent shit. And so he actually, when he graduated WPI, what did he do next? Anybody know? Anybody guess? I mean, you probably don't know, but you might guess. Yeah.
Did he invent something?
He did not invent something. But what he did do was go to law school. He finished WPI and then he went to law school. And he studied patent law. His theory was he still knew he wanted to invent shit, but he didn't want the patent lawyers to rip him off. So if he could become a patent attorney, then he couldn't get ripped off by a lawyer. I'm not certain the logic holds, but he is actually a patent attorney, and he works for a company doing patent law for them. And I have not seen him on any as seen on TV commercials or things, so I'm not certain if he ever invented anything. But a lot of us are here because we like to invent stuff. We like to make stuff. We like to take stuff apart to figure out how it works. And that's why a lot of us are here. Who's ever taken something apart and not been able to put it back together before? I think all the hands go up here, right? Who's ever done it with something that you weren't supposed to have taken apart? Yeah. Who's ever done it with a car? I mean, I put it mostly back together. It ran again, but there were definitely pocket parts. And those pocket parts, those are the parts that are still in your pocket when you put the thing back together and it still works. Those are pocket parts. They were unnecessary to the initial design. So this and so like you, I remember doodling as a little kid, designing personal helicopters. Who knew that 40 years later you could buy a personal helicopter? I didn't think it was that hard. I don't think it should have taken this long. I was going to use a lawnmower motor and a long shaft, and because I understood that helicopters moved because you changed the orientation of the wings, right? The wings are the things that spin around on helicopters. So I understood that if you change the orientation of the wings, you could go forward, go backward, go up, go down, right? You get to change the speed to go down or up. Yeah, so I was going to have this system of sliding weights that were controlled by levers. And I could pull levers back and forth, and I would transfer the mass to the front to tip the nose down to go forward. You guys, you've all designed it, right? Yeah. Anyways, so what is it when we want to design stuff and we go to college to design stuff? What's the first thing we think we need to know? So what's the first thing we think we need to know when we've decided we want to be a designer? Or even if you're not the designer person, you know them, because half the people in the room raised their hand. What's the first thing we need to know prior to designing?
The tools we use
for
designing.
So the tools we use, right? What software are we going to use for designing? Now, when I was a kid, I mean, by kid, I mean your age, they taught us how to roll the pencil in our fingers so that as we trace the pencil across the paper, the line thickness would not change. So what do you guys use? Solidworks? Mostly? Solidworks or AutoCAD or something like that? So how do you change the line thickness in Solidworks? You select the line and you right click and you say like change line thickness. Yeah. So if we wanted to change the line thickness, we had to pick up a different pencil. Because we had, like the 0.5 pencil and the 0.7 pencil and the different pencil sizes. So yeah. So I guess, what does that make us? Real engineers? Were you raising your hand or scratching your? Okay. Just checking. Okay. So we like to learn the software first, because the software is the tool that we use to do design. Is that correct? Is software actually the tool we use to do design? Software might be the tool we use to represent the design, but what's the tool we use to do design? It's our brain, right? We use this to do design. And you're going to interrupt me to talk about tomorrow's presentation? Because I told you to remind me in 2 minutes, 10 minutes ago. No, it was 10 minutes ago. You were supposed to remind me 8 minutes ago.
No, because the timer said a minute 50, so technically I have until 11.
Anybody else curious about tomorrow's whatever next week, Wednesdays, the next Wednesday's requirements? What's your name again? Simon. Simon says I need to tell you. I couldn't resist. So it's the first time we've ever done this assignment this way. In past years, you had until the last day of the term to hand in a written report that explained what you were going to make and how you were going to make it and how much it was going to cost and how you were going to repay that. We have next week and how many more weeks after that before the term's over? I hope it's one. You guys all hope it's one also, right? Okay. So I don't have anything scheduled for the Wednesday after next Wednesday. I think it's on the syllabus. It says final exam review or help. And Thursday the week after is the last day of class, right? And Tuesday that week, I said we're going to talk about design of safety systems. So first question, who wants to move the presentation to Tuesday of the last week instead of Wednesday next week? Raise your hands, be proud. Yes. If we keep them to 4 minutes like we did last time, we could. But that's a valid question. Who wants more than 4 minutes? Yeah, but who likes to talk? I like to talk. If you ask me if I wanted more than 4 minutes, I'd say yes. All right, so what I want you to do is so you've already said what you want to make and the process you want to use to make it. So I want you to tell me how much it's going to cost to acquire the equipment you need. How much it's going to cost to acquire the tooling you need. So if you're doing like CNC machining, you might need to buy tools and tool holders, things like that. If you're doing injection molding, you're going to need to acquire the dies for the injection molding setup. You don't have to make them because that would be like starting two businesses. That would be like starting a tool and die shop and starting an injection molding company, right? So any idea how much those kind of dies cost? A couple people said they want to do injection mold stuff. Yes. So it depends on the complexity of the part. $50,000 for the die set isn't an unreasonable estimate for a fairly simple part with a high volume production. But for low volume production, you might get a die for $4,000 to $10,000. So what's the best way to do that? I think if you're doing injection molding, Google the cost of making injection molding dies and have some rationale to back up the number you use. So cite some kind of a source. The source could be a website. That's okay. We're not, we don't need to go to what's primary sources or anything. We don't need to, go read the original text in Greek, ancient Greek. Anybody here study ancient Greek? No, I saw a hand flicker. Did you move your hand? No. I studied ancient Greek in high school to read Plato in the original. There was somebody else in my class that studied ancient Greek because they wanted to read the Bible in the original. But, the original version of the Bible was written in Greek. Anyways, okay, so how much is it going to cost to make the first part? How much is it going to cost so how much does it cost to make the first part means what's the startup cost to begin production? How much does it cost to make the second part? That means the per part cost after you make the first part. And at a reasonable selling price. So everybody's making something that there's a similar product available online. I don't think anybody's making anything that's so unique that there isn't a similar product. So survey the current pricing of products like that. Pick a reasonable price, something you wouldn't be embarrassed to tell your parents about at Thanksgiving dinner. Like, we started a company and we're selling these and this is how much we're going to charge. If you know that your parents are going to say nobody would ever pay that much, then don't use that price. And don't use a ridiculously low price, especially one that's less than what you think it's going to cost. And tell me how long it's going to take to make back how much it costs to start the business. All right, so that's what we already said, what we're going to make, where we're going to make it. So now I want you to tell me, how much is it going to cost to make the first part? How much is it going to cost to make the second part? So once you get into production, what's the per part cost? And what price point and how long will it take to pay back the cost of starting the business? We can do that in 4 minutes, right? So I think we can finish all the presentations in one day. Who wants to do it Tuesday, or who wants to do it next Wednesday, and who wants to do it the Tuesday following? Next Wednesday. Because the sooner you do it, the sooner it's over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The Tuesday after. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I suppose we should check if each group voted more than once. Since 12 people voted on one side and there's only 11 groups.
If we have to vote by group, can you give us time to consult our teammates?
Oh, no, I totally agree. But let's do Tuesday after. And next Wednesday, we'll talk about design and safety systems instead of the Tuesday after. That gives everybody a little bit more time. And it's not the last day of the term. It's the second day of the last week of the term. So it'll be good. And you only have 4 minutes. How many PowerPoint slides should you use in 4 minutes? 4 would be a good number. 3 would be okay. I mean, for me, it would be none, right? I haven't used a PowerPoint slide yet, except the one that was up to count down the timer. So what's the questions? What do you have to answer next Tuesday after? Go.
How much is each one going to cost? What's the price point? How long will it take us to make back those starting costs?
Right. So how much does it cost to start? What's the cost per part? What's the price point? How long will it take you to make back the initial? So you have to project sales, right? Yes. Right. That's how much does the first part cost? I just put it together. So you've got to get the equipment, get a lease on the property, get the initial stock. Maybe you pay something for design, or maybe you pay something for getting the tooling. Okay. Now, what were we talking about? Design for manufacturability? Okay, design for manufacturability. Here, slides. All right. So when people talk about design for manufacturability, they often think of design for assembly. And so we call this DFA, and there's books written about it. There's some famous professors actually from Brown and UMass Amherst who created this whole design for assembly thing. Boothroyd and Dewhurst, we call them, because that's their last names. And they talked about how do you design stuff so it's impossible to assemble it incorrectly. So assembly is a very important manufacturing process. Everybody agree? A lot of stuff that gets manufactured has some assembly step. And so some of the things they talk about is design. So if you get two pieces that have to fit together, design them so that it's impossible to put them together in the wrong orientation. So either make orientation irrelevant or make it so they only fit one way, right? So you put some locating feature so it has to go in. So any NASCAR fans? Anybody watch a NASCAR race this year? What was one of the major differences on the car that they used this year? So they used a single lug nut on the wheel. It's one of the major differences. And so in previous years in NASCAR, that just like your car that you drive, because they're supposed to be stock cars. Actually, in the beginning, there was people that go to the car rental place, rent a car, bring it to the track, change the tires, and go race the car, and then bring it back to the car rental place because they had crashed their car the previous week. I hope they paid for all the insurance. But now they're pretty custom. Anyway, so they went to this single lug nut to hold the wheel on, which makes it faster to change the tires, right? Everybody can understand why they did that. And like Formula One cars and Indy cars, they've had that single lug nut for a long time. But in the NASCAR, they wanted to make sure that the wheels actually went on. Because if it doesn't actually go on and it falls off on the track and it's going, say, 200 miles an hour and it hits you in the forehead, that's problematic. So, and so they have these little indent things, and it has to be aligned just right so that the pins go into the little holes they have in the back of the wheel. And if it doesn't, there's a little yellow thing that sticks out or whatever. So you can visually indicate whether or not you've got it on right. So they didn't make, I suppose if you flip the wheel around the other direction out, it wouldn't go on right either. I think that there's a visual indicator for that. Anyway, so they had some big issues with if you don't have it quite aligned just right, the wheel doesn't go all the way on. And then, you tell the car to go and then the wheel falls off and it's a big deal. So they were trying to use this idea of keying it so that you would know that it was correct before it left. Other things that go together only one way. You've all seen examples of this, right? Things that if you try to put it together the wrong way, it doesn't fit together. So that's one of the things. What else do you think would be a good thing for designing for assembly? There's a few rules of thumb. I think they're all obvious to you. If you're designing something that has to be assembled, what would you want to do?
Make sure that you can actually reach any bolts or.
Oh, so you're thinking of designing for repair, which car manufacturers don't do these days. Like make sure that you can actually reach the fastener to take the thing back apart again. Is that what you meant?
Or just put it together.
Yeah.
In the first place.
So make sure that all the pieces can fit together and you can tighten the fasteners, things like that. Who's ever taken some? We've all taken something apart, right? How many tools did you need to use to take it apart? I mean, unless you just used a hammer. One or two. If it was one or two tools, then it was designed pretty well for assembly. I've found that I can never find the right wrench. And the wrench that I have can never fit. So that's your point. Make it so that you can fit the tools in to do the thing. But if you're designing something for assembly, it would be really nice if all the fasteners were identical. So you didn't have to decide which fastener to use in which location. And you always use the same wrench to turn the fasteners. If you're designing something for assembly, those are the two big things. There's books about it. There's whole courses you can take on design for assembly. What I want to say is that design for assembly is not all that's important in design for manufacturability. And I want to talk about 5 things that you need to know before you talk to the cranky old machinist. And who's met a cranky old machinist? A few of us have. Here's what I know. If you're the spunky young engineer and you go to the machinist, no matter what they look like, what their apparent age is, what their apparent gender is, no matter what happens, if you're the spunky young engineer and you go there with your fabulous design, their favorite thing to do, oh, and it doesn't matter if it's an 18-year-old girl or a 57-year-old man, their favorite thing, they're all cranky old machinists, doesn't matter. Their favorite thing to do is make you exactly what you asked for, especially when they know it won't work. Because you're the spunky young engineer and you went there with your fabulous design and they know you don't know nothing. How do you fix it? So that they actually make, because remember, quality manufacturing is making what the customer needs when they need it. Now, why does the cranky old machinist make you what they know you don't need just because you asked for it? Well, partly because they can. Partly because they're tired of spunky young engineers with perfect designs. And I've been you. I get it. I've been the spunky young engineer that didn't know how to design stuff. They do it because they can. Because when you issue the purchase order and you attach the drawing to the purchase order, you have a contract. And you have to pay them to make the thing you designed that was poorly designed. And then you have to pay them to fix it. Now, it bothers me here working at WPI because I really don't want to make the same part twice or even help you make the same part twice. It bothers me here at WPI when people go outsource manufacturing and they get it made at a machine shop somewhere else without having designed it, and the cranky old machinist made exactly what they asked for, even though he knew it wouldn't work. And then you bring it back to me, and now it's my job to help you fix it. So it bothers me for those reasons. That's why I say it's sort of the bane of my existence. But what do you have to know? It's really easy. There's only 5 things, actually. 1, it will take longer than you think. Nothing ever happens as fast as you expect it to. So don't wait until you have to have the thing in order to ask somebody to make it. Here's one that seems kind of obvious. You have to actually know what it is you want to make. And this is more a WPI student problem probably than an engineer in the field problem. And when I designed these slides, it was actually to give presentations to WPI graduate students who were coming to me with their stupid, crazy ideas. Who's ever done a group project? You should all raise your hands because you're all doing one right now, right? So often in our group projects here at WPI, we design stuff. Sometimes the group decides to say, Pryor, you're the manufacturing person. Simon, you're the design person. And C, you're the person who, I don't know, leads them all. See, 3 names. Look at that. I'm pretty impressed myself. And so who's the manufacturing person? And so you come talk to the manufacturing people and you ask for help. Who's the design person? When's the last time you guys had an in-depth conversation about the design? A couple weeks ago? How much of it do you remember? Yeah, that's the problem. So when you go talk to the manufacturing guy, that cranky old machinist, and they say, if they're trying to help you, rarely, and I'm going to tell you at the end how to get them to try to help you. If they're trying to help you and they ask you, hey, could we make this radius not be negative? For example. Oh, by the way, do you know what they call you guys? All y'alls? Kids with CAD. Because it's wicked easy to draw stuff. That's why I asked the CAD question at the beginning. It's really easy to draw stuff. It's really easy to draw stuff that's difficult and expensive to make. So when the cranky old machinist is actually trying to help you prior, and they say, hey, could we make this be a chamfer instead of a fillet? And you say, I don't know, I didn't design it. It's like a stupid conversation, and they have no faith in you after that. So, wrong computer. This is correlated, highly correlated with the previous one. You want to know, why is it you're making it that way? And this sometimes comes down to like material choices. We're going to make it out of 316 stainless steel. Why would I choose 316 stainless steel? Yep.
You don't want it to rust.
Because it's highly corrosion resistant. It's non-reactive with a lot of different things. So marine applications and things that interact with the human body are often made out of 316 stainless steel. We're going to make it out of 7075 aluminum. Well, I don't know, because I guess it's a little bit stronger than 6061, and it's wicked shiny. 7075, right after you machine it, it is wicked shiny. You know what happens though? It oxidizes and it gets to be dull just like every other aluminum. But anyway, so you want to know, why did you make that material choice? Why did you make that radius choice? Those kind of things, so that when you're having that conversation, if the cranky old machinist suggests, hey, if we make this little change, it would be much easier to make, much cheaper to make, much faster to make, all those different things. You want to be able to answer that question when you're talking to them. Well, yeah, so this is sort of lines up again. So it's really, so far it's only two things, right? You need to know that it'll take longer than you think. You need to know what you're making, why you're making it that way, what you're going to make it out of. I mean, what you're making, why you're making it that way, and what you're going to make it out of, that's really all the same thing. But I've broken it into 5 steps. Same reasons. And you need to know that the design part of the process is your job, not the machinist's job. So when I was a kid with CAD, I was working for an engineering company that designed automation systems for manufacturing processes. And so one of the projects we designed, actually, who's ever used a plastic fork? Most of us have ever used a plastic fork. So when they make them, they come out on this big tree of plastic forks. They come out of the injection molding machine. And they're all just sort of attached by what's called a sprue, or a little stem. And so what they would do at the plastic fork factory is they would stack up 10 of those trees on top of each other. So just picture a whole bunch of plastic forks all lined up on top of each other. They'd stack them up, and as they described it to me, they hired a bunch of little Vietnamese ladies. It was in Worcester, and there's a large Vietnamese population in Worcester. And by the way, for technically difficult jobs, women are more detail-oriented on average. So for detail-oriented jobs, you want to hire women for that. So they hired a bunch of little Vietnamese ladies. But here's the process. Grab a stack of 10 forks in each hand, go like this, put them in the box. Grab the next stack of 10 forks, go like this, put them in the box. What's the problem with that? Anybody know? It's a lot of repetitive motion, and they were getting all kinds of workman's comp claims for carpal tunnel syndrome, because doing this all day long. I got my carpal tunnel syndrome from doing this all day long. I was operating a jackhammer. It was when I was a teenager. So it's not too early for you to get carpal tunnel syndrome. Anyway, so getting back to the design process is your part of the job. So we were modifying an existing design for a machine. So we made a machine that would automatically just degate those. So taking them off the thing is called degating. And so we made a machine to I don't want to say put all those little Vietnamese ladies out of work. I think we gave them a better job afterwards because there was plenty of work to do in the factory. But we'd had this little thing. It was a conveyor system, and it would bend them and drop them in the box all by itself. Anyway, while I was doing that job, I was asked to design some parts that were going to get sent out to the cranky old machinist to make. And I knew that I wanted to hold these two pieces of stuff together with a 1/4-20 fastener. So what's a 1/4-20 fastener? For people that don't know, yeah. So normally it's a 1/4 inch in diameter. That's the quarter part. Yeah. And the 20 means it's got 20 threads per inch along the outside of it. And so 1/4-20 fastener is a screw. For anybody that didn't know my terminology there, it's a screw and it's got 20 threads per inch and it's a 1/4 inch in diameter. And there's a standard depth for the threads and stuff like that. So when you want to put a 1/4-20 fastener into a part, you have to thread the hole. And so you can call that out on the drawing as 1/4-20 tapped hole, right? And you put a little arrow to it and you point to it, and that clearly defines that you want that to be a 1/4-20 hole. Now, the piece that mates to it, that the screw goes through, it can't have threads in it. If you put threads in both sides, they will never clamp together. And then it'll just be the fastener that's holding them together, and the fastener is not strong enough. The way these fasteners work is you tighten one thing against the other, and then it's friction between the two surfaces that actually hold the things together. The fastener loads in tension. So on my drawing, I've made a little note. I did my little call out. And did I say the diameter of the hole I wanted? No, because I'm lazy and I'm a kid with CAD. I just said clearance for 1/4-20. But picking the diameter of the hole was my job. I was the designer. And I sent it to the machine shop. And then my boss saw it. And that was the first and only time that my boss ever yelled at me at that job. I mean, he was like yelling at me. And I guess I got it. I learned the lesson. In my mind, the damn machinist knows what a clearance hole for a 1/4-20 is, right? He knows it better than I do. Except, what's the problem?
Well, you want to know, you specify how many,
It matters how much clearance, right? So there is sort of a standard drill that you typically use when it's a clearance hole for 1/4-20. And there's a chart that tells you sort of what the standard hole size is for clearance for 1/4-20. But the machinist doesn't know my design intent. So I may have needed a lot of clearance because I needed to be able to shift the thing around for alignment. The machinist doesn't know my design intent, and they won't know yours. So you got to remember that actually designing the part is your job. Yeah, so quickly, it'll take long. Yeah, I've used this presentation before, and I was supposed to quickly go through the first 5 things and then detail each one, but we talked about all these things, right? More slides. Oh yeah, so how do you avoid taking longer than you think? Well, just first know it. 2, when you go to the cranky old machinist and you want their help and you need their help because you know that you need help, because intelligent young engineers know that they need help with designs and choosing things like this. Don't say words like, we need this ASAP. What does ASAP mean? Yep. As soon as possible. What the heck does as soon as possible mean? Are you sure? You said as soon as possible. Well, for me, I got the game this weekend. I was going fishing next week. My daughter's got to play. I mean, as soon as it's possible for me to get away from the things I want to do, should I go work on it? Or wait, should I drop everything and even not go resuscitate the guy that needs resuscitation because your parts need to get made. Right? As soon as possible has no meaning. If you have a date that you need something, say, I need it by Friday the 18th. Who's not a freshman? Who remembers D term last year, last day of the term? What day of the week was it? It was a Thursday. It was a Thursday. What was the date? Oh, maybe I'm thinking of C term then. Or maybe I'm thinking of this term and I'm projecting forward. It was the 13th. Thursday the 13th. Maybe that's the end of this term? Oh, yeah, Thursday the 13th. What's special about Thursday the 13th? It uses a Friday schedule. So by some measure, it's Friday the 13th. All right. It'll take longer than you think. Yeah, don't say things like I need it. So this is a particularly important thing at WPI. Don't walk in. It's like, you have to make this for me. I have to do my experiment today. Doesn't move anybody. I've got my Solidworks all done. When can I pick up my part? It doesn't work that way. I need to show it to my advisor today. Yeah, no, it doesn't work that way either. I just need this one simple thing. This is probably my favorite. When you say, I just need this one simple thing, what I know is that you haven't designed your part yet and you don't know what you need. And you're going to be back over and over and over again. All right, so as the designer, it's your part to design the part, and then you have to convey the information to the cranky old machinist. What information do you have to give the cranky old machinist? They stop being cranky when they think you're cool. That's this really smart kid. I want to help that really smart kid. And again, it doesn't matter if they're 18 and you're 21. They're going to call you a really smart kid. If you are. You have to know enough to make the part. How does the designer tell us? Well, they could give us simply a sketch. I had a business once. We actually marketed online that we would take your part napkin to part. So if you came in with a napkin from the bar that's got your sketch on it, we would make the part for you. Now, it was going to be expensive because we had to do all the engineering because a napkin is not a design. But the first thing you need is a sketch. You need to have a concept of your part. You need to put dimensions on it, right? You need to clearly define what the extents of the part are. You need to define what's the surface roughness that you want. You need to tell us what's the material it's going to be made out of. And so if we look at this piece here, with the sketch provided, is there enough information to make the part? So I've told you the material is 6061 T6 aluminum. I've told you that the tolerances on all the dimensions are plus or minus 1/1000th of an inch. I've noted that the sketch is not to scale. So what piece of information is missing? Yeah?
Well, you can't make a perfectly square inside hole on a machine, right? So that you need.
So he says, I can't make a perfectly square inside hole in the machine. Who agrees with him? Oh, be proud. If you agree, hands all the way up. Be proud. Who disagrees? All right, so how do I make a perfectly square hole, Prior?
We'll start by drilling just some sort of like pilot hole and then maybe running it through an EDM.
All right, so he wants to use an EDM to make a perfectly square hole.
I mean, it's not going to be perfectly square.
Oh, now he's backing off on perfectly
For
square.
all intents and purposes.
So what's the problem with the EDM? You backed off. You know what the problem is, right?
Even that has.
So the EDM uses a wire. So the way this works, if you don't know, there's a wire and there's a base material, and the wire moves through the base material, but it moves through because there's a large voltage difference between the wire and the piece of material. And there's enough current available so that when the wire gets close to the piece of material, a spark happens between them. And anybody know that sparks are hot? Well, so it's hot enough to actually turn the material into like plasma, vaporize the material, make the material go away. And so you bring it over in this spark and you keep moving it. And as long as you move it at the right rate, it just erodes away the material. It just sort of vapor. You do it usually underwater, so it just the bits fall out into the water. That's a wire EDM. There's also a plunge EDM where you could have a shape like this that's electrically conductive, and then your base material, and you can just bring this close to the base material, and the spark thing happens, and you go away, and then you come back, and you go away, and you come back, and you go away, and you come back, and you can just make the negative of this shape in the part. It's actually how the molds for this mouse body were made, and I can tell just by the surface finish on the mouse thing, it was definitely EDM surface. But the problem is that wire has diameter. There will be a radius; it'll just be really small.
I was going to say a square broach.
You could use a square broach. So we've got our part here. We drill a hole, right? If you want to remove some of the material. And then you take apart another tool that's square like this, about the same size as the hole you want. And you just push really hard. And it pushes the material out of the way. Actually, saw a guy that was doing some material testing where they were testing compressibility of their samples. So they get this big instron and they put the sample in there and then they squish it. They're trying to see how much force does it take for the thing to fail when they're squishing it. And instead, they broached the bottom of the instron. They just pushed the part through it. The part was stronger than the machine. So I got 5 inches total, right? Oh, for the square. I think that's the Y dimension that's missing, but yes. We didn't actually say both dimensions on the cutout part, right? So there's a dimension missing. So what's the cranky old machinist going to do when there's a dimension missing? Whatever they feel like. Sometimes they stomp their feet and say, I can't make this part. That's not typical. Sometimes they just make it whatever size they want it to be because, hey, you didn't tell them. I think typically with the way this sketch is drawn, we would assume that it's square. And you could actually fix that by putting a little note on this one that says typical. And then it would imply that it was square. But yeah.
You don't say if you can make it out of 2 parts, because you could make it out of
Oh, that's the other way you could make that. That's the other way you could make it, is it could be 2 pieces. You could cut it right here along that edge. Take 1 piece and you can make a pocket in it that has that square bottom and then squish them together. So you could make it, so you could make this feature, but if you're the manufacturing person in the group and you haven't talked to Simon about why he designed it that way, you wouldn't be able to say, hey, could we make this as 2 pieces, right? But basically you need to give enough information that you can make the part. What are some things that you should avoid that make, so you can make square holes. They're more expensive than round holes, but you can make them. It's possible. And the smaller you need that radius to be in that corner, the more expensive it's going to be. Because even with a broach, after you use it once, those corners are going to wear out. And the other way you could do it is do it round and then use a file, right? You could file those edges. Yeah, all right, we did that. As a designer, what are some things you want to avoid? You don't want to be a kid with CAD. What do kids with CAD do? They draw features that are expensive to make. What should we think about? Well, so, all right, so what's the difference between a chamfer and a fillet? Yes. So a chamfer is like a straight. So if I wanted to chamfer this edge, I would make it go like that. If I wanted to put a fillet on this one, I would make it look like that. All right, so rule of thumb, rule of. Fillets are good on outside corners. Or sorry, chamfers are good on outside corners. Chamfers are not as good on inside corners. Fillets are good on inside corners, more expensive on outside corners. Let's think about it. So if we were going to cut this, if this was the z-axis, and we wanted to make that chamfer, what do? So if the part's coming out of the board towards us and we want to make that chamfer, we take a chamfer end mill. That's what you're going to say, right? Yeah. We take an end mill that's got a chamfer on it, and we run it along that edge, and we can make that chamfer. Now, what if I wanted to make this chamfer? What do I do? Exactly the same thing. I just have different offsets, right? Different step over to do that. What if I want to make this feature? Now, if I flip the part 90 degrees, I can just go around the corner, right? But if it's got to be in this orientation when I cut it, how do I make that shape? Yep.
You need a tool that kind of looks like this.
So I could make a tool that looks like this. And I could do it, and it's exactly the same as making this. What if I want to change the radius? I need another tool. So I could make a whole bunch of different chamfer sizes with one chamfer tool. But I can only make one radius with one radius tool. How else could I make this if I didn't have the radius tool? Yep.
You can flip the part 90 degrees.
I could flip the part 90 degrees, but if I can't flip the part 90 degrees for some reason, yes. I could actually take this tool, or more usually we take a ball end mill. So it's shaped like that on the bottom. And we make a pass. Then 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 we make a pass. And you get the idea, right? So I could interpolate around that shape with a ball end mill, like you did on your Y block, right? So we made that kind of a shape using, it was a bullnose end mill, but same thing. By going around that, you can make the shape, takes a long time. You can make the shape, takes a special tool. You can make many different versions of the shape, all with the same tool, goes fast. So that's why on the outside corners, it's nice to have chamfers. Now, if it's the inside corner, I put a chamfer there, it's the same problem as the square thing, right? But if I make this be a radius, which tool do I want to use? I want to use the biggest tool that I can fit in the feature, right? Because the bigger the tool is, the stronger it's going to be, the longer it'll last. So what's the biggest tool I can fit here? Is the one where the half the diameter of the tool is equal to that radius. Now in practice, we want to go just a little bit smaller than half the diameter. And that's because if it's exactly half the diameter, the tool path goes over here and it stops. It goes over here and it stops, and it goes over here and it stops. And at that instant where it stops, it just stops for an instant, but it's got to stop moving and then start moving in another direction. At that instant when it stops, it actually vibrates a little bit, and it creates what we call chatter. And so you get a crappy surface finish in the corners if you do that. If you take a tool that's a little bit smaller, the tool path goes around and it never stops, and you don't get that crappy surface finish from the chatter. So that's just a quick rule of thumb. Tolerances. Tight tolerances make better parts, right? Like tight tolerances means that the thing fits together better, right? The tighter the tolerance, the more expensive it is, the less likely it is to actually get made correctly. The more scrap you're going to have, the tighter the tolerance is. You actually want to design things with the loosest tolerance possible to make it still work. So avoid tight tolerances. Deep features. What's the problem with deep features? So really long, skinny holes, really long, skinny pockets, really deep, thin walls. What's the problem?
Say, chip removal and the chance of the tool being stuck breaking.
So chips coming out of the hole, when it's a long, skinny hole, it's harder for the chips to get out of the hole. You're cutting something like aluminum or brass or copper or something like that. The chips actually expand quite a bit because they get hot. And they'll actually, have we broken an end mill because we welded chips to the tool because we forgot coolant this term? Typically that happens in M1800. Somebody forgets to turn the coolant on or diverts the coolant, and it just doesn't evacuate the chips out of the hole, and all the flutes clog up with aluminum, and it just has no possibility to get out, and the end mill just breaks. Its cutting force goes way up. So chip evacuation is a problem. The other thing is we talked about stress and strain, right? We talked about deflection, and that length term is cubed. So even if we keep the same force, the longer the tool has to be, the further it's going to deflect with sideways cutting force. If we're drilling a hole, the bottom of the tool basically looks like that when it's coming at us. There's two little chisel tips coming at us, and then there's a spiral that goes up the drill. And so if one of these edges touches just a little bit before the other one, maybe it's not perfectly flat, and nothing is ever perfectly flat, it'll start the drill to deflect in that direction. Who's ever drilled a hole with a hand drill and a piece of metal? Who's ever had the hole go at the spot where they wanted to on the first try? Because you made a spot for the drill tip to follow, right? Yeah, so the longer the drill is that has to fit in the hole, and the narrower it is, so long skinny holes, the more it's going to deflect, the more likely it is the drill's going to break when you get in there. Deep features, thin walls. Thin walls are hard to make. Who thinks you should cut it close to the size you want, and then make a finish pass when they make a thin wall? That's typical when we want to do stuff. We make that finish pass because on that finish pass you can keep the cutting forces really light. Turns out when you want to make a thin wall, you don't want to have a finish pass. You actually want that last pass to be a big bit of material, because if you look at it, if this is our tool and it's moving sideways, if I've got just a little bit of material here, now this is the thing that's going to deflect. But if I've got a little bit of material here out where I already cut and a lot of material here, it's stronger at the part where we're cutting it. So it's not as likely to deflect. Yeah. Put the part in the machine as few times as possible. Every time you have to put the part in the machine is more likely that it's going to fail or you're going to make a mistake. I think that's it. Yeah, some materials are easier to cut than others. Chamfers versus fillets, yeah. But if you have just a second, my favorite YouTube video of all. Oh, there's no audio though. Anyway, the fishes are swimming around, and it's the first day of school for the school that Nemo's going to, and the little octopus character comes over. He says, "I'm H2O intolerant." It's my introduction to tolerances. My favorite YouTube video ever.
talking about the